Okay. So now we are in the chapter 5. Which is about the eigenvalues and eigenvectors. So as we have discussed, our matrix is always a square matrix, and we are interested in finding a vector x and a number lambda such that a times x is lambda times x. So in other words, I want you to understand the matrix A as a linear transformation from Rn to Rn, and this equation actually implies that once you plug in a vector x into your linear transformation A, then the resulting vector is going to be precisely always pointing the same direction, but stretched by the factor of lambda. Okay. We say the x is an eigenvector and lambda is an eigenvalue. And our convention is we usually require the x to be some non-zero vector, because if x equals to 0, if x is a zero vector, then everything becomes so obvious. So okay, so the question is why we are interested in the eigenvectors and eigenvalues. So here, we have a little motivation. Oops. Well, have you ever heard about the differential equations? Yeah, probably. Most of you must have heard about the differential equation at least once in your lifetime. Differential equation is, shortly speaking, the differential equation is a functional equation. So what that means, the solution of the equation is not usually a number, but solution is the function. And differential equation is a functional equation that involves the differentiation of the function. And here we are interested in not a single differential equation, but a system of differential equations. So let us consider this differential equation. So we are interested in finding the solution function y1 and y2 satisfying this relation. So y1 derivative is some constant times y1 plus another constant times y2, and y2 derivative is same. So constant times y1 plus another constant times y2. So if this guy equals to 0, suppose that if this guy equals to 0, then everything is obvious, because derivative equals to in that case the derivative equals to some number times itself. So therefore, in that case, y must be some exponential function, right? But in this case, y1 and y2, they are somehow intertwined together. So in this case, it is not very clear the solution of this system of this differential equation. And for this kind of differential equations, so we can write it in terms of the matrix. So y1 derivative and y2 derivative is this matrix consists of these numbers and times this column vector. Okay, nice. And this question is very much related to the eigenvectors and eigenvalues. Why? Well, I have a matrix. I have a 2x2 matrix here, and suppose that we were able to find a eigenvalues and eigenvectors of this matrix. Okay, so in other words, suppose that we found the eigenvalue lambda and eigenvector of this eigenvalue lambda. Then I claim that some constant times exponential function followed by lambda times t and times this column vector, times this eigenvector is going to be a solution of this differential equation. Why? So in order to be a solution of this differential equation, so if you want to verify if any given function is a solution of the given differential equation, then the fastest way would be just plug into each of these functions. Like, so if this is your dissolution, well, just take the derivative of this guy, y1 prime, y2 prime is, well, these are just some constants, so they just carries over. But e to the lambda t, so taken derivative is going to be lambda times e to the lambda t, okay? And so, well, so let me just switch let me just switch this location. If I send lambda to here, then lambda times, and we know then x1 and x2, they were assumed to be the eigenvectors of the eigenvector lambda. So I can replace this guy by this matrix times the eigenvector, okay? Then, moving this guy between the, moving this guy before this column vector x1 and x2, then what do we have? 3 times e to the lambda t times x1 and x2 is, we assume that this was y1 and y2. So just like that. So therefore, y1 derivative and y2 derivative is this matrix times the y1 and y2. Okay. So therefore, this guy is satisfying this relation. Therefore, this is a solution. Okay. Okay. So therefore, the finding the eigenvectors and eigenvalues is very much related to solving the system of differential equation, especially the constant coefficient differential system of differential equations. I can do even more than this. So, well, and if you have, suppose that you found 2 different solutions of this differential equation, then their linear combination still going to be the solution of the same differential equation, right? Because, you know, the derivative is linear. Okay. So we now want to find the eigenvectors and eigenvalues of the matrix A. So solution of AX is lambda times X. Well, here we are assuming that A is an n by n matrix. Okay, so since this is our definition of eigenvalues and eigenvectors, so this would be a very nice starting point of our computation. Then, well, so AX minus lambda times X must be 0 vector. And I can switch this one as lambda times identity and everything multiplied by X. Okay. And you have to remember that we are assuming that X is a non-zero vector. So that means, so to find the eigenvector, then eigenvector must be some non-trivial element in the null space of this matrix. This is, you know, this is an n by n matrix, right? So in order to have the eigenvector, then A minus lambda times I must be a singular matrix. Okay. So A minus lambda I is a singular matrix. And this is if and only if the determinant of A minus lambda I must be 0. Okay, so what is this? So now we are interested in finding the eigenvector. Sorry, the determinant of this matrix. Let me magnify this. Yeah, I want it to be red. Okay. So basically, you want to multiply. So you want to compute the determinant of this matrix, and also, well, since we are interested in finding the eigenvectors, eigenvalues, so first therefore to find, well, we are interested in finding this unknown lambda. So I can say this is an equation for unknown the variable lambda. Actually, in fact, this is an polynomial for the lambda, right? And can you identify the degree of this polynomial? What is the degree of this polynomial? You know, this is an n by n matrix, and I have lambda here. The lambda appears on the diagonal entries of this matrix, right? So, and well, basically, you are supposed to compute the determinant of this matrix. So, well, and in order to compute the determinant, then for every row, every column, there must be exactly one entry has to be chosen. So therefore, you're supposed to have the n factorial many terms in this computation, right? And every row and every column and each of these n factorial many terms, then every row and every column, it must contain exactly one entry, right? So, and the lambda can appear at most n times when you're computing this guy times this guy times this guy times like this. Okay, so well, if you multiply this, then you can find the lambda to the n term out of this. Okay, and lambda cannot appear more than n times, right? So therefore, this is the polynomial of the lambda with degree n. So this is we say this is a we call this guy as a characteristic polynomial of A. And this equation, we say this is characteristic equation. And characteristic polynomial is degree n polynomial. Degree n polynomial. Okay, so this characteristic polynomial plays the crucial role in finding the eigenvectors and eigenvalues. So, therefore, in order to find the eigenvalue of the matrix A, then first you are supposed to solve the characteristic equation, and the root of this characteristic equation should be the eigenvalues of your matrix A. Okay. Now, and once you found an eigenvalue, then how would you find the eigenvectors of the eigenvalue? Then once you found the eigenvalue, then you plug in this your eigenvalue here, then A minus lambda is going to be a singular matrix, and the vector in the null space of this matrix is going to be a eigenvector of the eigenvalue lambda. Okay, so there is an exercise here. Let us find the eigenvalues and eigenvectors of this matrix. So the first of all, we are supposed to solve the characteristic equation. So what is the characteristic equation? So is 4 minus lambda minus 5 and 2 and minus 3 minus lambda and 4 minus lambda and minus 3 minus lambda and this minus this guy times that, which is plus 5. Oh, not 5, sorry, plus 10, sorry. So this is lambda square minus, is it lambda? Minus 2? Yes. Okay, so this is the characteristic polynomial. Yeah, clearly, and as we have expected, so whose degree is precisely 2. Okay, and we want to solve this characteristic equation. Well, this is easy. So lambda minus lambda plus 1, lambda minus 2. So factorizing this polynomial, so we have this. So we have two eigenvalues, which is minus 1, and the other one is 2. Okay. So for each of these eigenvalues, we want to find the eigenvectors of these eigenvalues. So let me start from the eigenvalue -1. So AX is minus X. Therefore, A plus I is the 0 vector. So that means, well, basically I am plugging in lambda equals to -1 to here and there. Then 5 minus 5 and 2. Is it minus 2? So we want to find a null space element of this guy. So, well, basically, we are looking for the x1 and x2 satisfying this equation. Well, even though it looks like I have two equations, but there is, well, essentially I have only one solution, or only one equation. X1 is x2. Okay. So basically, so every vector, so every number satisfying this relation can be a eigenvector of eigenvalue lambda minus 1. But, well, our convention is we can just choose whatever you want. Just choose anything, the easiest one. In this case, I have chosen 1 and 1. So because I believe this is the easiest pair of numbers satisfying this relation. So I say so. So now I declare this is an eigenvector of the eigenvalue minus 1. However, so if I say this is the eigenvector of this eigenvalue, then you must consider that any linear combination of that eigenvector can be you should automatically consider any linear combination of this linear eigenvector can be automatically another eigenvector of the same eigenvalue. Okay. And sorry. So there I have found only one linear independent eigenvectors, but there can be more than one linearly independent eigenvectors for a single eigenvalue. So yeah, we'll go back to this issue later on. But well, anyway, so in this case, I have found only one linearly dependent eigenvector. So now let me turn to eigenvalue 2, positive 2. Then AX is 2 times X. So A minus 2 times I, X is the 0 vector. And so basically, I'm plugging in lambda 2 here and there. So 2 minus 5 and 2 minus 5. Oh. And x1, x2. So I have 2x1 is 5 times x2. Therefore, the second eigenvector of the eigenvalue lambda 2 is so, well, here I have a freedom to choose a number x1, x2, but I guess the easiest pair of numbers x1, x2 satisfying this relation is going to be 5 and 2. So this is an eigenvector of eigenvalue minus 1 and set. All right. This is another interesting exercise. And this exercise involves the system of differential equations. And suppose that we are interested in finding the solution of this system of differential equations. y1, y2, y1 derivative, y2 derivative is just like that. Okay. Shall I change this in terms of the matrices? So y1 derivative, y2 derivative is 4 minus 5 and 2 minus 3. And y1 and y2. Okay, so we now know how to find the system of this differential equation. Well, so solution is actually the e to the lambda times t times the eigenvectors. Okay, and we know the eigenvalues and eigenvectors of this matrix. So therefore, y1 and y2 is some constant times e to the, so we had two different eigenvalues, minus 1 and 2. So e to the negative, so first eigenvalue was minus 1. So e to the negative t, negative 1 times t, times whose eigenvector? The eigenvector of the eigenvalue negative minus 1 was 1 and 1. So 1 and 1. And well, I should be choosing another constant. And the another eigenvalue was 2, right? So, and the associated eigenvector was 5 and 2. Okay. So these two guys can be a solution of this differential equation. Well, So and I told you, so whenever you found any two solution of the differential equation, then their linear combination could be another solution of the same differential equations. So therefore, this guy plus this one is a solution. Okay. Okay, good. Well, so far so good. But actually, the problem is asking us even more than that. So we are looking for the solution specifically satisfying when t equals to 0. Yeah, well, so your solution function y1, y2 or the function of t, and it says the solution must satisfy y1 0 equals to 8 and y2 equals to 5. Okay. And in this case, so these constants C1 and C and D, they are undetermined, right? So these two guys, these constants, they can be anything. So in order to satisfy this initial condition, y10 and y20 is, so you're asked to plug in t equal to 0 into the right hand side of this equation, and so this is 0 times, so this c times 1 and 1 plus d times 5 2, and using the matrices, well, this equation can be written like this, and it has to be 8 and 5. And so we require the resulting column vector should be 8 and 5. Okay. So in other words, we need to solve the system of equations of 2x2 equations. And well, this is not a big deal. You can do this. So after, so it is not easy to find the C is 3 and D is 1. So therefore, so let's see, was it 3? Yeah. And what is the solution. Okay. Okay. So by doing so, we found the solution of this differential equation satisfying this very specific initial condition. Maybe, so if you're paying attention to this lecture, well, maybe you can ask yourself, oh, is it the unique solution? Well, in other words, can I find another solution of the same differential equation satisfying the same initial condition? And the answer is no. Well, there has to be always one unique solution satisfying this very specific differential equation and the initial condition. So this is the solution. Okay, but that is the another story in another time, maybe. Like if you're interested in this kind of topic, then you should register yourself in for the differential equation course, but which is not very, so we are not gonna go into that detail in this section, in this course. And also, eigenvalues of diagonal matrix are always the diagonal entries of the diagonal entries of the diagonal entries of the matrix. And in this case, the eigenvectors are the standard unit vectors. Okay, so what does it mean? Well, this is a diagonal matrix, and I am finding the determinant of a diagonal matrix minus lambda times the identity. So basically, this is the characteristic polynomial of this diagonal matrix. Okay, and well, and computation is not complicated. So 3 minus lambda times 2 minus lambda, so which is this, and if this guy equals to 0, then okay, you can easily convince yourself that there are only two solutions of this equation is 3 and 2. And so these are eigenvalues. And as you can see here, these eigenvalues are precisely the diagonal entries of your diagonal matrix. And in this case, if you multiply the first standard unit vector, 1, 0, here, then the answer is 3 times of the first standard unit vector. So therefore, the first standard unit vector is the eigenvector of this eigenvalue. And as you can see here, so well, the eigenvector of eigenvalue 2 is the second standard unit vector. Okay. So so diagonal matrix is I think the diagonal matrices are the easiest kind of matrix in computation of the eigenvectors and eigenvalues. Okay, and the another also there's another example about regarding the projection matrix. A projection matrix has eigenvalues 1 and 0. So do you remember the projection matrix? Well, suppose that you are interested in finding, so you're in the R, the ambient dimension of the ambient space is Rn, and suppose that you wanna find a projection matrix which project everything into the k-dimensional subspace of Rn. Then how would you do that? You will just find the basis, the k basis of the k-dimensional subspace, and using that you can build an n by k matrix, right? Then A times A transpose A. Yeah, I'm kind of messed up. Yeah, A times A transpose A inverse times A transpose. Yeah, that is the projection matrix, right? Okay, you know what I mean. So you know how to find the projection matrix. And suppose that you found such a projection matrix. Okay. And what is the dimension of the projection matrix? Yeah, even though your projection matrix is not full rank matrix, it has to be always rank k matrix, but its dimension is always n by n, right? So therefore, you must be able to compute the eigenvectors and eigenvalues of your projection matrix. Always. And it claims that the projection matrix, the only possible eigenvalues of the projection matrix is always either 1 or 0. There can be no other eigenvalues for the projection matrix. For example, I have this this is a one-dimensional subspace of we regard this as a one-dimensional subspace of R2, and what is the projection matrix that project onto this one-dimensional subspace? This is the easier one. So A transpose A times A transpose. So what is A transpose A? So 2, yeah, 2 and This is everything is 1, 1, 1, 1. And 1/2. So everything divide by 2. So this is your projection matrix. And to find the eigenvalues, P minus, I want to find the determinant of P minus lambda times I. So which is 1/2 lambda and this is 1/2 minus lambda squared and minus 1/4. Okay. What is this? Lambda minus 1. Am I right? And we want this guy to be 0. Oh, okay. Oh, okay. Great. So, well, this computation says that the eigenvalues are 0 and 1. Why is it true? How can I prove this? Yeah, I can spend time and effort to prove this, but well, I have a better explanation. Well, why? Because of this. So, well, for any vector, suppose that you are projecting these 3-dimensional vector into this 2-dimensional subspace. And if your vector belongs to this 2-dimensional subspace, then the projection doesn't change anything. So this vector multiplied by this projection matrix is going to be this vector itself. Right? Because of this reason, this vector can be considered as a eigenvector of eigenvalue 1. Because P times this vector is this vector itself. And on the other hand, what about a vector that belongs to the also orthogonal complement of this guy? Suppose that you want to multiply this vector to the projection matrix. If you multiply P times this vector, then the answer is the 0 vector. So this vector can be considered as a eigenvector of eigenvalue 0. That's it. And there can be no other possibility. There is no other option. You cannot stretch any vector by 2 or something like that. There is no such thing. So because of this reason, the projection matrix has eigenvalues 1 and 0. Okay? Great. Right? And A has well, I told you, so the eigenvector should be a non-zero vector, but that does not imply 0 cannot be an eigenvalue. So 0 can be an eigenvalue of some n by n matrix. And so you can imagine, maybe you can try to write down a matrix whose eigenvalue equals to is 0. And I claim, suppose that A may have many different eigenvalues, right? 1, -2, 100, 1 million, anything you imagine. And I claim that if your matrix A has at least one 0 eigenvalue, then that implies that A must be a singular matrix. Right? Because having a 0 eigenvalue implies A times eigenvalue X equals to 0 times X, so which is 0. So that means you have just found some non-trivial non-zero vector that belongs to the null space of the matrix A. Okay. And I believe some of you already recognize this, but I have been intentionally avoided mentioning the complex numbers and matrix with complex entries. But okay, at this point, I can no longer avoid mentioning the complex matrix with complex entries. Well, even if all entries of A are real, but there can be a matrix whose eigenvalues are complex numbers. Why is that? Because of the characteristic polynomial, the characteristic equation. Characteristic equation, well, suppose that your matrix A has all real entries, then n by n, then whose characteristic polynomial is a degree n polynomial of lambda whose coefficients are all real numbers. But even if the coefficient of degree n polynomial are also all real, but the root of the polynomial can be complex numbers, right? Because of the reason, the eigenvalue can be a complex number. Okay. I have just came up with very important example. Just like this is a 2x2 matrix, very easy matrix, and whose entries are all real numbers. And let me try to find the eigenvalues of this guy. Then, well, determinant of minus lambda, minus 1, 1, and minus lambda. This is the characteristic polynomial, right? And it turns out is lambda squared plus 1. So whose eigenvalues are plus and minus imaginary unit I. Okay. In this case, in such case, when your eigenvalues are your two eigenvalues are the complex conjugate to each other, then your eigenvector must have some complex entry inside. Well, for the eigenvalue I, let me try to find the eigenvector. Then since lambda is I, so here I'm plugging I and I here. So minus I, minus 1, 1 and minus I. I am looking for the vector x1 and x2 such that multiplied equals to 0. Okay. Then minus I times x1 minus x2 equals to 0, and x1 minus I times x2 equals to 0. Yeah, even though it looks like I have obtained two different equations, but actually they are linearly dependent. Why? Can you see this? If you multiply minus I to the both sides of this equation, then you're going to get the first one. Okay. So, well, basically, so you have only one equation. So, well, don't be scared of the complex numbers. Yeah, even though we are now computing the matrix with some complex entries, but their computations are all the same thing. So there you have nothing to worry about. Well, except for the Hermitian inner product. Yeah, the inner product is completely another story, but okay. I'm not going to mention about it for now. So for the computation, the determinant and the computation of the eigenvectors and eigenvalues, they are so you should be considered exactly the same way as you did in the real numbers. Where was I? So okay, so x1 is so is it I times x2? Yeah, okay. So whose eigenvector is So yeah, as always, there can be many different choices for x1, but I will choose the easiest one, 1 and I. Yeah. And number 2, what about I is -1? Then in this case, now we want to solve this equation, and I find by the same computation, I have x2, which is 1 and, oh, sorry. I messed up. I'm sorry, forgive me. And 1 and I. Okay. Okay. So, well, so I mean, the point is there's nothing to worry about. Everything is just the same. Okay. All right. Okay. Let me take a coffee break for like 5 seconds. Now, I want to talk about the basis and basis changes. Yeah, I know you're not the huge fan of changing the basis, but well, this time I really have to mention about it. Do you remember this? I have a linear transformation from Rn to Rn, and yeah, my choice of notation was not that great. These E1 from En, so they are not the standard unit vectors in this case. Sorry about that. So they are just some random choice of basis. I have 2 different choices of the basis for Rn, and if T of these basis vector, well, I can write down this vector as a linear combination of these bases. So, and in this case, well, I can represent, there is a matrix representation of this linear transformation with respect to the basis, B1, and from input basis is B1 and output basis is still B1. And you know how to find this matrix. So just all you have to do is nothing but just writing down each of these entries one by one in this vertical manner. So I will say this is my matrix A, and same thing is true for the basis B2. If T of F, if I can write down T of Fi as a linear combinations of these bases, then this matrix representation of the same linear transformation, but using the basis B2, so this is B2 and this is B2. So input basis is B2 and output basis is again B2. And yeah, so like this. So, and let me say this is matrix B. Yeah, even though the matrix A and B, they should look completely different, but you have to recognize that they are actually referring to the same thing, same linear transformation, right? So so the question is, for any given 2 n by n square matrices AB, how do you know that 2 different matrices are referring to the same linear transformation? Those 2 different matrices A and B are referring to the same linear transformation if and only if you can find the another non-singular matrix M such that A equals to M inverse times B times M. If, in other words, if those 2 matrices are similar, okay? If 2 matrices are similar matrices, then they are referring to the same linear transformations. Do you remember this? No? Okay. All right. So this is the idea. So, well, if this is the basis vector from the basis B1, if EI, I can still write down the EI as a linear combinations of F, the basis vectors F, and just like this, then, well, this is, I say this is the matrix of the change of basis matrix. Then this identity matrix can be written as the input basis B1, right? And output basis B2. And again, so this writing down this matrix is also very easy. Just look at all these coefficients and plug in these coefficients into the ith column of this your matrix. Then this is going to be your matrix M. So this is change of basis matrix M, and clearly this one has to be non-singular matrix. Okay, so this guy, so this matrix inverse times matrix B times the matrix M should be the matrix A. Okay, so therefore, so in other words, for this given matrix A and B, I was able to find another non-singular matrix M such that M inverse times B times M equals to A. So they are similar matrices. So they are referring to the same linear transformation. Okay, so this is my question. Okay, so imagine this hypothetical scenario. So you just found two different square matrices. They have the same dimensions. They are all n by n. How do you know they are similar matrices? Finding out this matrix M out of nothing is almost an impossible task to me, right? For any given two random matrices, A and B, can you find such a matrix M? Or can you even prove that there is no such matrix M? Yeah, this is very hard question. And in order to answer the question, I have a partial answer of this. Well, you can try to find the invariant of the matrix. So what is an invariant? Invariant of matrix is like this. And so invariant of matrix is considered as an algorithm such that imposed on the n by n matrix M, so that applying that algorithm that you found some number or some couple of numbers, well, a number or couple of numbers or something like that. And so applying the algorithm should be easy, relatively easy. And once you compare the invariant of the matrix A and invariant of matrix B, and if those two numbers are different, then it can be an evidence that those two guys can never be similar matrices. These are the notion of invariant. Like, on the other hand, so invariant is okay. In other words, invariant is like this. Every similar matrix must produce the same invariant, but not the other way. But not the other way around. Two non-similar matrices can have the same invariant, but I mean the same. Sorry. Okay, so okay. Let me correct myself. Yeah, the similar matrix. If you can find an invariant such that every similar matrix produce the same thing, same invariant, then that is considered as a, well, that is an invariant. That is an invariant. So what is the example of the invariant? I think the determinant is very interesting and most useful invariant you can find on the n by n matrix, right? Why? If two matrices are similar matrices, then the determinant of these two matrices, these two matrices must be always the same thing, right? But however, I can think of two n by n matrices whose determinant are the same thing, but they are not similar. That is still possible. So determinant is something like a prime example of the invariant of the matrix. And today, I want to introduce another invariant of the matrix. So another invariant of the matrix. The characteristic polynomial is independent from choice of basis. So it is an invariant of matrix. So in other words, if A and B are similar, then characteristic polynomial of A is the same as the characteristic polynomial of B. Why? The proof is easy. Determinant of A minus lambda I is the same as determinant of M inverse times A minus A, right? Right? Because the determinant of this guy, determinants always preserve the matrix multiplication. Determinant of A times B is the same as determinant of A times determinant of B. So this one has to be this. But M inverse A times M lambda I. Okay. And this is determinant of B. So if A and B are similar matrices, then their characteristic polynomials are always the same thing. So characteristic polynomial is an invariant. Okay. So the characteristic polynomial is an invariant of the linear transformation. So therefore, that means a root of a characteristic polynomial, in other words, the eigenvalues, also must be the invariant of the linear transformation, invariant of the matrix, right? Two similar matrices must share exactly the same set of eigenvalues. Okay. And since the characteristic polynomial is an invariant, therefore, every coefficient of the characteristic polynomial also must be the invariant. Right? Isn't it too obvious? Let A be an n by n matrix. Its characteristic polynomial is this is its characteristic polynomial. And I said this one has to be the degree n polynomial. And what do you think is the leading coefficient? So the degree n term must appear, so should appear only if you are multiplying these and these diagonal entries. So there has to be minus 1 to the n factor times n. So this is the leading coefficient, and C n minus 1 lambda n minus 1 and C1 lambda 1 and C0. So this one is the characteristic. So I say each of these coefficients from Cn minus 1 to C0, they are the invariant of the linear transformation. Invariant of the matrix. And number 1, Cn minus 1 is minus 1 to the n minus 1 times A11, A22, ANN. So what is this? This is simply nothing but the sum of all diagonal entries of the matrix A. So I can smell this. The sum of diagonal entries of the matrix. Well, determinant is a very nice invariant of the matrix, but the sum of diagonal entries of the matrix also can be a invariant of the matrix. Two similar matrices must have this exactly the same. If you have the similar matrices, and suppose that you are taking the summation of all diagonal entries for both of the matrices, then these number always must be the same. If you're believing in this claim, okay? Okay, so let me prove this. The determinant A minus lambda is, well, so you're basically, so it consists of n factorial main terms, and how this, and each of these terms is like is given by taking multiple, choosing for each row you're choosing one column, and then once you have chosen this column, then for the later rows you cannot choose this column anymore. So, and once you choose this guy, and for the third column you cannot choose column number 1 and number 2. So you have to choose another column like this. So for each of these rows you're choosing different columns. And because of this reason, you must have the n factorial many terms from this computation, right? This is the nature of the determinant. And well, so I will have A11, A22 minus lambda. So therefore, first term that I can think of in this computation is, for the first row, I am choosing the first column, and for the second row, I am choosing the second column, and for the third column, third row, I am choosing the third column, and so on. And so this is the first term that comes in my mind when in computing the determinant of this guy. Okay, and I claim this guy times this guy times this guy times this. If you multiply all these negative lambdas together, then you're going to get this one, right? So this is the only way that you can achieve the leading coefficient in this degree n polynomial. And I claim that in order to obtain the Cn minus 1, which is the coefficient of the degree n minus 1 term, can be obtained by, can only be obtained from this term, can only be obtained from this term. Why? Because suppose that if I choose this one, this column for the first row, then I cannot choose the first column anymore, the second column anymore. So therefore, for the second law, so how do I explain this? So, well, if I choose this guy, then choosing this guy as an entry is completely, this possibility is completely eliminated. And choosing this guy for the entry is also completely eliminated, right? So whenever, no matter which column you choose for the first law, then you're automatically getting rid of choosing the possibility of this guy and that guy, so that guy, right? So therefore, all the other terms in this computation can involve at most n minus too many terms, diagonal terms, right? So therefore, all the other guys are the terms of degree at most n minus 2. Okay? So if you factor out this, then if you expand this and minus 1 to the n times lambda to the nth plus minus 1 to the n minus 1, a11, a22, a times lambda n minus 1 and plus all those terms of degree less than equals to 2. Okay. So because of this reason, Cn minus 1 is this. Okay. And number 2, Z0 is precisely the determinant of A. You know, this constant degree 0 term here is always should be the determinant of the original matrix. Why? This is even easier to show. Determinant of A minus lambda I is, you know, this guy. And why don't we just plug lambda equals to 0? Then determinant of A should be the constant C0. And so now this is the right time to introduce you to this definition. For any square matrix A, the sum of its diagonal entries is called the trace of A. And we'll usually denote this by TR of A, the trace. And there is a very interesting theorem. Well, suppose I have this many eigenvalues of this n by n matrix. So I have the eigenvalues from lambda 1 to lambda n. Well, if you have if your characteristic polynomial contains some multiple root, then there could be the same eigenvalues in this list. But well, anyway, but eventually you're going to get up to counting the multiplicity. You're always supposed to have the n many eigenvalues for this matrix n by n matrix A, right? Then if you take the sum of all these eigenvalues, then this is always the same as the trace. And if you multiply all those eigenvalues, then it is always the determinant. The this is your characteristic polynomial, which is a minus lambda times I. And this is which is this. And well, in the field of the all complex numbers, I can linearly factorize this degree n polynomial like this: lambda minus lambda 1, lambda minus lambda 2. In complex numbers, you can always linearly factorize this polynomial, degree n polynomial, which contains these exactly n factors. And if you expand this polynomial, then you have lambda to the n minus lambda 1, lambda 2, lambda n, and times lambda n minus 1 plus da da da. And the constant term is going to be lambda 1, lambda 2, lambda n. Okay? So comparing this, multiply this guy by this term, this vector, this number. So minus 1 to the n plus 1 times lambda 1, lambda 2, lambda n. This is precisely, this is has to be Cn minus 1. Okay? But Cn minus 1 is this guy. Okay? So this is minus 1 n plus 1 to the n plus 1 is minus 1 to the n minus 1. So anyway, eventually, so is A11, A22, ANN, which is the trace. Okay. Likewise, so this time, let me multiply this guy with this. Then minus 1 to the n's, minus 1 to the another n's. So minus 1 to the 2n. Oh, just forget it. It's just 1. Is lambda 1, lambda 2, lambda n. This is 1. This one has to be precisely C0. Okay. But we know that this is the determinant. All right. So this is a corollary. The trace and the determinant are the invariant of the linear transformation. So you can play it like this. You can play this game like this. Choose if you suppose the two random n by n matrices are given. They have the same size. They have same size, and suppose that you are interested in finding the similarities of these two matrices. And if the trace and determinant are all the same, then those two matrices may be similar to each other. But that does not guarantee those two matrices are similar. But on the other hand, if at least one of these two invariants are different, then that is a clear evidence that those two matrices can never be able to similar to each other. Okay. Okay. And I just ran out of time. Okay. So this is for today, and see you next time. 여기 여러분 친구들 중에 혹시 오늘 예비군 간 친구들 있어요? 예비군 분명 있을 텐데, 그러니까 예비군 한 친구들은 거기 관련 서류 저한테 제출하면은 오늘 퀴즈 한번 본결로 빼드릴 거거든요. 네. 네.
베이시스 체인지 하시면
예.
로테이션
네네네.
마지막에 이 ID EF가 교수님께서 이걸 EF로 주고 F랑 G로 적었는데
예.
이 EI는 ID EI 하실 때 이 EI 둘 다 이 T에 이 베이시스 하나의 EI는 그
똑같은 친구죠.
소위하는 그